Well, hello, everybody. Going to be talking with you today about moving from monolithic transactions to distributed sagas in an event-driven architecture. I'm just going to start out with a little introduction. My name is Israel. I work in an application architect role at a company called Avanade, where we do software engineering best practices and help clients modernize, move architectures from the monoliths to new event-driven patterns, as well as cloud migrations, a lot of different things. So my most recent experience and expertise has been in the event-driven space, mostly using Microsoft technologies and the Azure cloud platform, but I've also been partnering and working with Solace on a couple engagements. I live in the Seattle area with my family and 3 daughters. Just a little bit about Avanade. We are a joint venture with Accenture and Microsoft. It started around the year 2000, and we do all things Microsoft technologies for clients from the Office 365 all the way to custom software development running in the cloud and Azure. So anyways, back to the topic at hand is starting with talking about transactions and monoliths. So this is basically a computer science 101 kind of concept about how we can handle transactions and keep in line with the ACID principles, right? Most of us are familiar with the ACID principles: atomicity, consistency, isolation, and durability. So traditionally, this meant we have a single database. The single database can help us maintain that data consistency. So in my example, I have confirming a reservation, processing a payment, decreasing inventory. All that can be done in a consistent way within a single database, utilizing transactions. The atomicity is guaranteed because it's all as one unit, all or nothing. And our relational databases help us provide this functionality kind of out of the box, right? We just leverage those transaction models and things just work. In this model, mainly we start to think about certain concerns such as scaling up, as our application runs over time. Our data may grow, our demand may grow. So scaling up our database is a concern. Replicating the data is a concern. We need to make sure we don't have any data loss for production systems. But the question is, what do we do once that scale up limit is reached? And what if we want to move from a monolith to microservices, which are becoming very popular? So in order to solve those challenges or move to microservices, we basically have to start thinking about some new solutions and patterns. So in this example, I'm going to take what I just used with this kind of transaction. And in an EDA world, we might think about moving this into multiple microservices, right? So a reservation service, and we might use a queue kind of intermediary between that and a payment service. Payment service could process the payment, keep track of that record in its own database, and then an inventory service can help manage the inventory. That's kind of an idea of how that might look in a more EDA type approach. But then we have to consider how we deal with atomicity. So now we have things distributed with different databases, and how can we handle that being looked at as one atomic unit? One idea is to introduce something called a transaction manager. A transaction manager, though, may need to implement something like a 2-phase commit. This is one approach to solving this problem. And in this scenario, we have a lot of communication calls. We have to request from the service, and they have to vote yes or no, and then go down the line, and then we have to commit each one and keep track of whether the commit succeeded. And there's quite a large chance of things failing in all those communication calls. So is there a better solution? I'm advocating for yes. And that better solution is Sagas. And we'll talk a little bit about what a Saga is, how it's helpful. And basically, we need to start by thinking about transactions a little differently. And actually, I think this model is even closer to the real world. In the real world, we don't have transactions that are atomic in the sense of a database. They're not normally atomic. It's more like you hand someone some money, and they may give you an action, a product or service in response, a reciprocal action. Similarly, if you pay somebody, they don't fulfill their obligation, you might try and get a refund or get your money back. So this is kind of the more real world model that Sagas kind of fit and align to. So we want to start thinking of our transactions as a set of actions with a set of compensating actions that actually unwind it if things fail. So that means the system is always going to work even when something fails, and we are going to have a record and a way to handle all those failures, even things that happen outside the system, like a product failing to be delivered by a delivery service. We can still handle those types of failures. And so by treating everything like a state machine, we can model all this, and we can record, like I said, all the details about failures and rollbacks, which is unique than the traditional transactions because those typically don't have a record of all the things that happened that went wrong. So what is a multi-step transaction called? I'm glad you asked. It's called a saga, a long story account series of incidents, also known as a chain of events. So our sagas just transactions? No, they're not transactions in the typical sense, in that if they fail, there's no trace. If a saga fails, we don't remove all those records of things that went wrong. We just initiate compensating actions to help kind of revert what happened. And we can also tolerate partial failures in this scenario. So an example might be if a failure, if something fails to send an email, we might be able to tolerate that error not being reproduced, or something along those lines. We have way to model that within our business. So essentially just a different way of designing these systems. The question is, are they new? And actually, no, they came about in the 80s in a white paper, a computer science white paper. But originally they were prescribed as a way to handle non-atomic transactions in a single database. And later, when microservices came around, there was a new concept of a distributed saga that has gained in popularity. That's what this is based off of. So what does it look like? We just break down our transaction into a set of steps, like I mentioned. We're going to execute them in turn. For each step, we have to have a corresponding compensating step. And then when a failure occurs, we have to make sure that those compensations are executed. So in this example, we might book a hotel, book a car, book a flight, take payment, and then those would all have compensating actions to cancel or refund payments. So there's a few rules to sagas in order to ensure things work as expected. The first one is all the steps have to be idempotent. So we have to make sure that we can run a step multiple times without causing effect. This has to do with essentially processing and error handling. If a step fails to process and we have to pick it up again, then we have to be able to process that idempotently. We also have to make sure our steps and compensating steps are commutative, which means the order doesn't really matter. Generally, we can't guarantee order in all scenarios of all the steps in this distributed transaction. So we want to make sure we can execute them in any order without dependency. And lastly, the compensations must never fail. So I'm going to talk more about that, but we have to have a way to handle all the compensations to ensure things work as expected. So I'm going to apply this to a travel system example, kind of along the lines I was already explaining. We're going to go through an example of being an online travel agent. Most of you are familiar with this type of scenario. So starting out, we have here in our example, a hotel service and a payment service. So the website sits in front of those two things. And the question is, how can we make sure the hotel gets booked and a payment gets taken, but never allow one without the other? So we might think of first putting in a little workflow in the website. Website would call the hotel service. The hotel service would book the hotel. The website would call the payment service, and so forth. Payment would be accepted through the credit card system. So, but what could go wrong in this scenario? In this process flow diagram, you can see with all the different steps of communication, there's quite a lot of potential failure points between the website and the hotel service and the hotel, and down the line. Another approach would be to take the hotel service and make that an aggregator. So the website calls the hotel and the hotel service kind of handles the workflow from there. Just a slight variation. Website goes to hotel books the hotel, and then calls the payment service. Similarly, what could go wrong in this scenario? Well, as you can see, there's not a whole lot of difference. We just shifted responsibility from the website to the hotel service, but we still have a lot of potential failure points. So next, if we were to think about adding cars and flights, kind of rounding out the whole travel experience, we see a lot more lines of communication here. And then we have a few added questions. So who does the website call first? What order do services call each other? What if I want a flight but no car? There's a lot of combinations, a lot of complexity, and a lot of failure handling to implement. So again, from the previous example, if we had to do something like a two-phase commit solution, we're getting kind of exponential in our growth of communication calls, and the likelihood of failure along that path is getting larger and larger. So the distributed Saga idea says we should introduce a Saga execution coordinator. This is a new component in this pattern. And essentially this has the business logic built into it for managing that workflow. It logs all the commands and every reply that it gets. And it can, if there's a failure point, it can kind of flip the things in reverse and start working backwards to compensate for all the things that have already happened. So it's essentially, in the computer science world, this would be considered a state machine that's modeled in an acyclic directed graph. So we have a starting point, we have an ending point, and there's different flows and how those, we can get from point A to point B, but there's always a starting and ending point. And some of you may be thinking this is like a process manager pattern, but Sagas are different than a process manager because the focus is on failure handling and not managing a complex workflow. So that's our goal here, is to make sure we're focusing on the failures. So back to this model we had earlier, this example, we now introduce this Saga execution coordinator on top of all these services. And it's essentially a state machine, as I mentioned. A few key things of this SEC component is it must be strongly consistent in its storage. This becomes a very key component in the overall reliability of our system. It needs to have what's called a Saga log, so its own data store for this Saga execution, so it can keep track of all the actions that have happened within the flow. Here's an example of that log. You might start booking the hotel, end booking the hotel, start booking a flight, and so forth. It's going to log each of these steps to that Saga execution coordinator log. And I already mentioned it needs to be very reliable. And generally, the order shouldn't matter because they're either all completed or they're all compensated. In the example with a failure, we might get all the way to a payment, for example, and things fail. And then we have to start thinking of compensating all the things that have happened already. So in that little animation, you see we get all the way to payment, and then we start compensating payment, compensating car, flight, etc., kind of backing out all the things that have happened. So that's basically the concept. This is the distributed Saga pattern, and it uses this SEC component. However, I will say in my experience, this isn't always how we build something. In this example here, we have some what we call bounded context around these different services. We have things that seemed aligned to a given domain, like hotel, flight, car, and payment. But then we have this other thing called the SEC that kind of sits outside of all those bounded contexts. And well, not really sure what we might do with that at this point. It has a lot of business logic in it. So where does that belong? What do we do about this component? So my recommendation here is that we actually call this something called a trip. We come up with a higher level aggregate concept. And this is in line with what you might see on other travel website providers, is really what we're doing is we're orienting all these components like flights and cars around a larger concept called a trip. That's what you actually are starting to build or search for on your trip page. So it is commonly implemented, even though it's not in that Saga pattern documentation. So what we can do here is we had originally defined these bounded contexts here, and now we can make the Saga execution coordinator part of our trip bounded context. So that's what I'd recommend we do in this scenario. We can even explore the trip domain concepts with things like event storming, which I'll talk about later, as a way to understand and define what that business domain looks like outside of just the execution log itself. And we can actually build this log a little differently. I'm getting to next. So we can build this log as what's called an aggregate root. And this is an example of that, a simplified example of that object kind of serialized to JSON. And as we go through this Saga workflow, we're going to update the state of these components that are part of that Saga and make sure it's stored durably. So in this example here, I'm going to see we might start with booking a plane, changing its status to started. When the booking of the plane completes, we mark that status as complete, and so forth. Starting complete, starting complete. Oh, we got to a failure. Now our overall status for that trip is going to be aborting. We're going to start compensating things that have completed at this point, aborting the hotel, or compensating the hotel, compensating the car, compensating the plane, and overall, our trip overall status is now aborted. We've finished that full Saga execution. So I would suggest that we also model these Sagas as events. So kind of is in line with some of the things we've already been talking about. Sagas can actually be sent and received as what you call integration events or commands. So an example of this would be a car booking requested event, or a car booking succeeded event or failed, and then corollary, the car booking abort request and aborted event kind of fits in line with the sequence of that state machine changes. A couple other things that are key, like I mentioned earlier, is the idempotency. So in order to provide idempotency of requests, we have to make sure that each event in this scenario is uniquely identifiable. So we just need make sure we have unique IDs on these things. One way to do that is to utilize the relevant business ID, because you're going to have to store it anyways, like something like a trip ID or a custom ID and version number as a kind of aggregated unique identifier. Otherwise, we're all used to generating GUIDs or other unique identifiers and adding that to our events. With those unique identifiers, we can leverage those for making sure events can be processed only once or processed with idempotence, so it's not going to have any lasting effect on reprocessing, and we can store those in our databases and in our logs. So I mentioned we can't let compensation events fail, compensation steps. So in this example, if our car service for some reason can't talk to our car system, it disappears completely for a time, what do? Well, the car service needs to own this as the first thing. They need to own that communication. They must keep trying. So you might implement something like a exponential back-off pattern to, if it's a transient error, try again later, maybe try again after some additional time. But we should also set a time limit. So how long can that go on for? That might coincide with the SLA of that API or provider you're talking with. And ultimately, you may need to alert a human in the end. So this all goes back to how we model this overall business process. But in the end, something has to happen to handle the compensation event, and we can't just log that as an error and move on. We have to handle that process somehow. So I'm just gonna go into here a few thoughts on how we enable this. I've talked a lot so far in just kind of the pure pattern, because it really is a design pattern. It's not suggesting any particular implementation, but there are a few things that help in the overall implementation, including an event broker, which I'll get to. But I want to start with talking about domain-driven design. So in our experience, domain-driven design is very helpful to model these appropriate service domain boundaries to discover the bounded context, along with the concept I mentioned earlier called event storming. This is where you model out all the state changes and events within your system, and that in a room together with all the business and technical stakeholders. Many people might be familiar with this term. It was created by someone named Alberto Brandolini, and this helps us define those bounded contexts we described earlier. It's not always clear, like hotel service and car service, and et cetera. We can help model an existing business domain, and that also leads us to what the boundaries are and what events make sense to be crossing those boundaries. So it leads us right into kind of modeling our events in an event-driven way. And this aligns with our overall theme that we believe business software is successful when it aligns well to the business domain which supports it and has minimal coupling between the components. So if the team that's building it has good alignment into these domains they support, there's a good chance of success. As I mentioned before, these patterns are not implementation specific, but there are a few things that help, such as message brokers. So there's quite a number of those, including Solace's own PubSub Plus. Many know there are others, such as Kafka or the Azure or Amazon native ones, Azure Service Bus or EventBridge. But each of those are built with different capabilities and for different purposes. The other thing that helps is a good hosting model for these services. We'll talk about that in a minute. Kind of PaaS or serverless versus a container-based hosting model. And then finally, monitoring. So we want to have good monitoring and observability, especially as we get into a more distributed system. So on the event broker topic, I just want to mention that event brokers definitely help with some key challenges as things like implementing the Saga pattern and event decoupling in general. So decoupling obviously makes a lot of sense. We can have better isolation rather than point-to-point calls, which can have failures. The event broker allows for that intermediary. We also can have reliable messaging. So we can actually have these events produced by one service and consumed by another in a very reliable, sometimes called guaranteed messaging way. And the little asterisk there is just to imply not every broker has this capability. Kafka, for example, has more guarantees on ingestion, but not necessarily the same protocols which have additional acts in them to acknowledgements to ensure the messages get delivered to the consumer as expected, which Solace does have. And then durability. So once events are placed on the broker, there's persistence and durability. So we don't have to worry about those events getting lost once they make it to the broker. It also enables some other patterns, such as ease of scaling or sharding, better observability and extensibility, and then enables us to do some real-time processing. Event sourcing is another pattern, and also wiretapping. So things like hotel service publishing an event. In the future, we can extend that by a new service down the line, consuming that event, or wiretapping into an existing event stream and be able to build new functionality. There's a lot of benefits there. And then on the service hosting front, there's definitely a lot of popularity in the serverless model approaches of the AWS Lambdas or Azure functions, and they definitely have some benefits. The other option would be a more standard web endpoint, like an ASP.NET backend or just a web job running in the cloud or on your on premises. But we've had a lot of good examples of using containers. So any hosting model where you can actually have a consistent connection to a broker, basically a permanent running job that can keep a connection to the broker, actually can help in optimizing, especially with the AMQ style brokers, because they can maintain a connection and have very efficient notifications when new events are ready to be consumed, rather than the serverless model, which sometimes has to pull events on some cadence, and you don't necessarily get the same optimization there. And lastly, monitoring. So most of you are probably familiar in a distributed system. We're now taking our central database and services and spreading them out. We no longer have a single log source for looking through all those transaction logs in one place. So observability becomes a little more difficult, but there are techniques for centralizing that logging that should really be taken into account prior to go live. So make sure this is something thought of up front. There is an industry standard that's been developed called OpenTelemetry, which is vendor agnostic and allows for logs, traces, and metrics to be sent into various tool sets. There's a lot of them on the market. Some of them are good for on-premises, some are cloud native. It all depends on your deployment plans. And if you build on a kind of abstraction like OpenTelemetry, you also can route those logs and traces to different providers depending on where you're running it. So you might run something on locally on-prem and have it go to one source, and then deploy to the cloud and have it go to a Azure Log Analytics or Datadog, for example, and then be able to correlate all your logs together in one place. So in closing, I've mentioned a lot about the Saga pattern. So some of those key enablers is to design your services appropriately, utilize things like event storming to design those boundaries and surfaces. Make sure to leverage an event broker that can definitely help to implement some of those concerns, and an efficient hosting model in the cloud or otherwise, or containers. Embrace the Saga pattern. It's definitely a great, reliable way to implement transactions in a distributed manner with microservices, and designed for your observability up front. Thank you all for your time.